Hello guys, my name is Intae. I'm a co-founder and CPO of Vessel AI. Thank you for coming and I hope you enjoy this evening. Yeah, a little bit of my company and myself. So Vessel AI is focused on building the best AI infrastructure platform for developing AI faster at scale. So we are focusing on the AI infrastructure, the middle layer between the hardware layer and the application layer. So our platform is pretty much end-to-end developer platform for training and deploying full spectrum AI, including large language models. The customers including Hyundai Motors and Scatter Labs. As you can see from these customers, we are from South Korea. From this year, we're trying to expand our business in US. After I study at University of Texas in Austin, computer science, I started my career as a machine learning engineer. Now I'm working as a head of product for this MLOps platform. So what do I want to cover today? For 4 years, we're doing business and we meet a lot, like tons of customers. And the ultimate goal of the enterprise customer is to build a complete machine learning operation system. And particularly nowadays, it has to be the private LLMs feature. So today I talk about why enterprise want private LLMs and how we approach this problem. It could be a little bit of concept of fine-tuning and RAG, but also I touch some practical experiments and results. Also, I'll give you some insights from our experiments. So private LLM. So basically, private LLM means we're starting from the foundation models, usually open source models, and train the proprietary data and self-hosting them in their own infrastructure. So enterprise, there are like 3 reasons why enterprise want private LLMs: privacy, control, and cost. Some of the company wants their machine learning sits in the on-premise server or at least private cloud, and data it should be in the stored in the secure way. And the control, they want the response from the prompt should be controllable. I mean, the hallucinations or everything, like the response from the LLM is usually fluctuated, but at least in their own domain, like legal, health, or finance, they wanted the control. And for the cost, if you're using GPT-4, it costs like $50 per million tokens, but they want to be cheaper than GPT-4. So our goals today is to build a smarter model than GPT-4, at least in my domain and context. Also, get a cheaper, cheaper costs than GPT 3.5. So private LLM make smarter, faster, and cheaper. How we can achieve this goal? For smarter, we can do fine tuning, but not just a fine tuning, but I'll introduce some techniques or open source libraries to how we fine tune the model. For the RAG is actually pretty much like a open book test. So I'll introduce some of the techniques we're using for RAG. And I'll talk a little bit about the quantization and caching and fine-tuning. So there's a rumor that if you're training a relatively small model, like 7 billion parameter model, still remains expensive if you train from scratch. It will cost you like 300K if you train from scratch. But yeah, but if you fine-tune the 7B model, SLLM model, it actually, it's not that expensive. So the enterprise interested in fine-tuning because the prompt engineering itself is not enough. So they already tried some naive RAG, but it doesn't work pretty well. Also, they want particularly like domain expertise or structure outputs like JSON or YAML. I mean, the output wants to be structure outputs. So the text is slightly small, but this is a little peek from our experiment. We test with a little bit of prompt engineering to generate the criminal sentence from Mistral 7B model. The base model is Mistral 7B model. As you can see from the beginning and the end of the response, we have some response, not the JSON format. I mean, we particularly ask large language model to output the JSON output, but it's not aligning with prompt. Also, they have a wrong answer. Well, here is the history. We give the history for the criminal sentence, but we only gave LLM one example, so they output the wrong answer. It's the hallucination. However, after we fine-tune with 10 million tokens, they have a correct JSON format with a correct criminal sentence. So how do we get there? So the common technology nowadays is called parameter efficient fine-tuning, PEFT. It's actually like open source libraries from Hugging Face. Yeah, it's a basically you don't train every 7 billion parameters for the fine-tuning. You just pick the important numbers. Like, for example, the LoRa, which means the lower rank of adapter. So as long as this training works on GPU, it means the data is zeros and ones, which is the matrix or even matrix of matrix tensor, right? So if you recall the linear algebra from your college, the matrix has certain, some numbers are more important than the other ones. So we care about those important numbers, and the LoRa is, we're gonna fine tune those numbers, not the all numbers in the parameters. We freeze the rest of the parameters. And QLoRa is the even faster method. The Q stands for quantize, so I'll talk a little bit about quantize later. And there's also another variation called DORA. As you can see from this first diagram, in the lower rank, it gives like dramatic accuracy improvement, like 20 to 30% accuracy. So we would like to experiment LoRa, QLoRa, and DORA with the criminal sentence data set. And we're using the tools called Unsloth, which will optimize GPU memory. And it usually like 2 times faster than the vanilla fine-tuning. So the data set we're using is open data set from LBox. It has 10 million tokens, approximately like 6 to 7 books. The data looks like this. And we're using L4 GPU. It's not that high-end GPU like 800 or H100. The reason why we choose L4 is they have enough memory, like 24 gigabytes GPU memory, but also we can easily get these instances from cloud service like Google Cloud. So we choose L4 GPU for this particular experiment. And the foundation model was Mistral 7B. And I want to introduce one of our features called Vessel Run, which is defined by YAML definition. So as you can see here, we're gonna run this model with GCP Oregon region with L4 GPU. We're gonna pull the code from GitHub, which has the LoRa or QLoRa like training code. We're gonna pull some data set from Hugging Face and also Mistral 7B here. After training, we're gonna export, which means the upload this trained model to Vessel artifact, which is this the storage in our platform. Once you get this YAML file, you can send the HTTP request to our server, and our server will translate this YAML definition into Kubernetes YAML manifest. And then it will create the machine learning workloads to Kubernetes. It could be GCP or AWS, or even your on-premise server. You can change a single line like Vessel, GCP, Oregon to whatever cluster you want. And you can easily change the GPU, the number of GPUs, like you want to use like 2 L4 GPUs or whatever. Also, you can easily change the foundation model. And then it will find the instances in the Google Cloud Platform, the L4 GPU, and then pull all the codes, models from GitHub and Hugging Face. The good thing about this YAML definition is that you can have this all configurations, so it's really easy to reproduce. And as I said before, it's the unified interface across all the cloud providers, so you don't really need to study GCP or AWS. You just have to specify everything in this YAML definition. So here's the results. So our baseline models gives like 27-ish performance, and GPT gives like 55%, but the fine-tuning model, we actually scoring 50 evaluation samples on the 0 to 2 scale, and it gives like 20% better than GPT-4. GPT-4 actually hallucinates or returns very generic outputs. Sometimes it doesn't align with JSON outputs, and it almost every time they give like wrong criminal sentence. For the performance-wise, we tested QDORA, and OnSloth, but there's no clear winner between the LoRa and DORA in cost-wise. The training time is almost same, but the performance-wise, DORA is slightly better, and OnSloth tool gives you 2 times faster with 50% less virtual RAM, GPU RAM. So the key takeaways from the fine-tuning, obviously garbage in, garbage out. So if you trying to implement fine-tuning, you have to first care about your data sets. After that, it's not that expensive as you imagine. It's for our particular experiment, it costs you less than $10, which means, we're using 5 to 6 books. With the L4 GPU, it will run 4 to 9 hours. It depends you're using OnSloth or QDORA or DORA, and it's roughly less than 10 hours. But if you want to training more data sets, it will still be under $100, I would say. But you still need to prompt. Like prompt adds another level of accuracy. I'm not particularly testing prompt engineering in this experiment, but especially if you care about the JSON output, you have to do some prompt engineering. Okay, that's it for the fine tuning. Everyone talks about RAG right now, and a little bit about the concept of RAG. RAG means retrieve the relevant information from the vector dataset, a vector database or knowledge source, and augmented those prompts from those retrieved data to generate answer with augmented query. So why do we use RAGs? Our customer usually think that RAG is easier than fine-tuning, because for the fine-tuning, people think that you need machine learning engineers to handle all these things, but RAG, all you need to do is put everything in the vector database, whatever, it could be your image or PDFs, like tables or whatever. And as long as you have your reference data, it will reduce the hallucination, and ultimately you might think it will control over the output. However, naive RAG doesn't work really well. So simply throwing your documents into vector database doesn't work pretty well. First of all, you have to think about the indexing. So how would you split the data? Think about the PDF file you want to throw into vector database. If the chunk is too big, there will be too many contexts, or if the chunk is too small, retrieval doesn't really work. So you have to find the sweet spot between this data chunk size. How would you handle the images or codes or tables, right? You have to think about this pre-processing part before actually embedding to the vector database. Also, it may not be 100% accurate, which means, after all, it's based on the embedding similarity, not the prompt similarity. So actually, you have to re-rank those results I'll talk about later. But yeah, there's like naive RAG doesn't really work. So here, like advanced RAG, you need a pre-processing part or post-processing, or there's like lots of techniques out there, re-ranking or hide, I'm gonna say like augmenting data sets or augmenting prompt. But as a platform developer, what we are interested in is modularize those techniques and make it as a product, right? So today I'm gonna introduce 2 techniques of RAG, but that's not the only techniques outside there. For this slide, RAGS is one of the open source libraries to evaluate RAG. It uses large language model to evaluate large language model. We know large language model is still slow and unreliable. It's less than 80%, but the more important thing is that it's faster. It's still faster and more efficient than human, right? So RAGS is commonly used to evaluate RAG problems. And right-hand side of the diagram, also it's a small, but here on the top performance combination, they're using Cohere re-ranker or hide. I'm gonna talk, two techniques today. Okay, so the first approach to improve RAG is context augmentation. You can augment questions or you can augment data sets. For the questions, generate the hypothetical document, which means you don't do RAG, but just using your prompt to generate the hypothetical document first. So take the prompt and the hypothetical responses, and then you pull everything to it's called contriever, then maybe it will improve your data set. And it turns out it works pretty well. That's the method called hide. And the second method is augmenting data set, which is we call Raptor. You cluster similar documents and store a summary of the documents as a new document. So these are all the recent papers from NeurIPS or recent machine learning conference. So if you're more interested in this topic, go the links there and check out. But there's a lot of techniques. Every single day, there's another improvement technique. So you should follow all those RAG techniques. And then re-ranking. So re-ranking is actually not a new concept. It's a common in recommendation system. They're using a lot of re-ranking in the recommendation system. It starts with on the assumption that performance improves with useful information at the top. So among your prompt, the order does matters. If something on the top of your prompt, maybe that's more important information to generate your response. So you have to re-ranking the results from the RAG. So one of the key players here is Cohere, one of the foundation model company. They offering re-ranking API. I mean, it's not that difficult to implement this re-ranking model. So keep in mind to try some of the re-ranking. And here is our results. We put everything, fine-tuning and RAG into one chart. So yeah, as you can see, with the RAG, the performance goes up dramatically, but still fine-tuned model is better than GPT and way better than baseline model. However, this accuracy comes at a cost because this hide and re-ranking, the hide approach, you have to request to LLM once more. I mean, you have to generate the hypothetical documents, right? So there's like a trade-off between the accuracy and the latency. So that's actually the second bullet point of that. You have to care about the trade-off. So if you care more about the accuracy, you better, you might be compromised some latency there, but if your service is more care about the promptness, like a user experience, then you might have to keep up some accuracy. And the RAG, garbage in, garbage out would be the first and the foremost important things. You have to cleansing, pre-processing your data set well for the RAG, but after that, you can apply hide or re-ranking on top of the RAG. And finally, the quantization part. I'm not going deeper for the quantization, but we're using the common technique called AWQ, which means the compress the weights, like into 4-bit. This means, for example, like a floating number like pi, it's like 3.14159 or something like that, right? But we're not going to use all those numbers, but we're rounded up at some point to use like 3.1 or something like that. That's how the quantize actually works. So it will save your memory and improve the inference speed dramatically. And we saw it will improve like 5 times faster. And for the cache wise, we're using flash attention and page attention. Flash attention is parallelize the attention operates, and page attention using KB cache, which means key value cache. I mean, these are the key feature from the VLLM, which is the famous framework for serving machine learning models. So we're using both of them. And these are actually easy to implement. You don't have to really understand the flash attention, how the flash attention works or page attention work. Like the open source libraries like text generation inference. I mean, there's still there. It's like changing the arguments. Yeah, it's pretty easy to implement. So you have to test this on your own data set or on your business, that how it works in your business. For the results, the quantization and flash attention gives us 5 times faster performance. So the numbers here, like if you're using L4 GPU, for the Mistral 7B, it will handle 500 tokens per second and 75 concurrent requests thanks to the VLLM. It roughly gives you like $0.3 to $0.4 per million tokens, which is cheaper than GPT 3.5. So yeah, that's how we approach this RAG and fine tuning. So you got your own model. Now you have to choose you're using RAG or fine tuning or even both techniques. As I said before, there's some, trade-off, and you have to compromise some tricks based on your business. But there's a common thing you have to keep in mind is that if you have a complex procedure, you need like reproducibility. You have to set up the automated pipeline, like CI/CD pipeline, let's say for indexing or fine-tuning, and yeah, focusing on prompting, like monitoring, see if like the logs, like Jackie mentioned before, and then your update models gradually. And here is the sample architecture. I put everything together on this diagram. On the top, this green line is a pipeline. It's an indexing pipeline, which you throw your data set to the vector database, and this second green square gives you like fine-tuning pipeline. And then you have like vector database in somewhere, and you also need some service endpoint with this blue boxes here. On our platform, we call it vessel run, vessel serve, and vessel pipeline, which is the series of vessel runs, and vessel artifact is pretty much like a storage on our platform. So yeah, here's key takeaways. Like if you have a baseline model, well, many customers rather choose GPT. However, if you fine tuning a RAG, accelerate them, it's better than GPT-4, at least for my domain. You can make your MVP less than $100. And yeah, it's doable in consumer GPUs like L4. It's less than $1 for less than $1. It's pretty fast and relatively cheap. That's pretty much it for today, but you might think it's still challenging and don't know where to start it. Maybe you can talk to me after this pitch and the networking session. It's just a little bit about our product. But yeah, as I said before, we are focusing on the middle layer between infrastructure and the application layer with vessel run, serve, and pipelines. So yeah, if you're interested in our platform or the technology we're using, feel free to reach me out. And yeah, thanks for.
Since we're a little short on the time, we'll get one question from the audience.
Thank you. That was super interesting. I wonder if you could just elaborate on your definition of private LLM, because it's now possible to have your own private endpoint, for example, in Azure of GPT-4, and many companies would consider that private, even though it's using a proprietary model. That data won't be trained on, and the token is yours. It's not going to be used, that endpoint, by anyone else. So I wonder if you could just elaborate on that, maybe decouple open source from private, because I think the two are used interchangeably sometimes incorrectly.
Yeah, that's a good question. Well, I use open source term as it's open publicly. You can download it, the checkpoints or weights from the Hugging Face or anywhere. But some of our customers like Hyundai Motors, they want to keep everything inside their infrastructure. They don't let any HTTP requests outside of their platform. So we package our platform as everything inside this application. So we don't let any HTTP requests outside the platform. We download all the Docker image inside the infrastructure, and all the models they're interested in, download it there. That's how we approach it right now. Thank you. Yeah, we're scoring like 50 evaluation samples. It's accuracy. Yeah, you can imagine like 0 to 2. 0 means like they have a wrong JSON output or something like that. Yeah, we manually put them into 0 to 2 scale, and then spread out to the 100.
Do you come up with some
categorical
to come up with accuracy? Because translation, how will you do that?
We define these evaluation metrics, not the.
I see.
Yeah.